Tell me you're no good. I'm brushing away, do you? The weight of you, of my shoulders. Done with my cigarette. And when all the smoke is clear, I'm brushing away, do you? The weight of you, the weight of you. Don't need a no man. Tell me you're no good. I'm brushing away, do you? The weight of you, of my shoulders. Done with my cigarette. And when all the smoke is clear, I'm brushing away, do you? The weight of you, the weight of you. Don't need a no man.
Good evening and welcome everybody. This is Obi-Wan Pezwar and Simplex Pachinko. We are going to be working on some cracking the GRE, one of those two books. And we're going to look at specifically two sections. One is on decomposition of partial fractions, or partial fraction decomposition. And the other will be on definite integrals. So, we're going to hop right into it. Apologies for this. I came back to a Firefox update, and when I restarted my computer and restarted Firefox, it came back with the usual 3 windows that were sized properly on the entire, screen. However, it only had one each a new tab. So all of my history is still there, but I don't even know what open windows I had. Yeah, that gets to be a little bit tricky sometimes. We are going to let me export the image because I definitely forgot to do that. Okay. This was chapter 12. 12 on evaluation. Okay, good. And reset our canvas. Normally I do that after the stream and not while I'm trying to get the next one set up. But hey, whatever. Okay. So last time we were talking about partial fraction decomposition. What we were really concerned with was trying to make sure that we could get an integral to then be broken up instead of having one fraction that was quite impossible to work with. What we could do is come up with a much nicer version of this integral, which is going to get us the exact same answer. So, a little bit challenging sometimes. It's not actually too bad, but what we're trying to do here is we're trying to say, is there anything that we can do to try and split this thing up, make it a little bit easier to work with? This right here, right, x squared plus 3x plus 5 is a quadratic, and it is shifted upward 5 spaces, and then our b value swings it back down such that the y-intercept will still be at 0, 5. However, the 3 is not a very large number. And so if we look at the determinant of this thing, this is going to be b squared minus 4ac. B squared is 9 minus 4 times a is 1, c is 5. That's minus 20. So we've got a 9 minus a 20 is negative 11 as our determinant. So we end up with the square root of negative 11 in part of the quadratic formula to try to find our zeros for this particular quadratic. So that's not going to work for us. So this is not factorable. In the rationals. Right, it's not actually factorable in the reals at all, but we don't really care. If it's not factorable in rationals, then you're probably not going to get something nice out of it anyway. And you're just going to have to use the quadratic formula, honestly. And the other one, on the other hand, x squared minus 4x minus 5, has a minus 5 as our a times c, and then the only factor pair that we have is 1 and 5. This is going to tell us that the sign of the larger number has to be negative, and this one tells us that the signs have to be opposite each other. So they have to have opposite signs. The larger one has to be negative, therefore negative 5, positive 1. Okay, so when we split that up, we end up getting our, and again, we could do this the long way, where this is going to be x squared plus 1x minus 5x minus 5, and then common is x, left over is x plus 1. Minus 5 is common, x plus 1 is left over. So therefore this is x minus 5x plus 1. However we're going to do it. Okay, so this is still x squared plus 3x plus 5. And then this breaks up into, let's go x plus 1, x minus 5. That is not an I promise. Alright, so when we do this, this gets us 3 distinct terms that we're going to work with here. And realistically, what we want is that this thing is going to break up as 3 separate terms. So we should get an integral that is going to look like a over x squared plus 3x plus 5. We'll come back to that in a second. No, I can't come back to that in a second. We got to deal with it now. Okay, this cannot just be a constant, because it is possible when we do our division. We talked about this last time. When we do long division here, if we had a quadratic up top, we'd still be able to divide the quadratic on top by the quadratic in the bottom and get a constant multiple of it in some way, shape, or form. So here, if we end up with a linear term, ax plus b, divided by our quadratic in the denominator, this is going to allow us to have, I also wanted to do another one, but we'll get to that. Could have done it all at once. Not the point. Okay, so what we have is an irreducible or unsimplifiable or unfactorable quadratic. So the numerator could be as large as a linear function. That could be what remainder we get out. So we're going to assume that it's going to be as big as possible, right? As big a remainder as possible. Can't still be a quadratic, because we could divide a quadratic by another quadratic. It could be a constant, but it also could be a linear function when we stop doing all the division. Okay, then we want a second term, which is going to be c divided by x plus 1. In this case, this has to be just a constant because our x plus 1 could divide into another linear term with some constant multiple. And then we get a d divided by x minus 5. Right? Same reasoning. All right, and then we just stick the dx on the end and let it be contained in all this stuff. So what we really want at this point is that this, our ax plus b, divided by x squared plus 3x plus 5, plus c over x plus 1, plus d over x minus 5, should be equal to 1 divided by, and that's where this comes in. Our original fraction that we had up here, if this was a like 4, then we'd want that to be a 4. Not a 41. We'd want this to be a 4. Right? If this was a x plus 2, then we would want this top part to be x plus 2. And then we just copy the denominator. So whatever's there is just getting copied over. We want to split this fraction into these parts. So got all these parts. 1 divided by all that stuff is going to get us these broken up bits. The linear divided by x squared plus 3x plus 5, constant divided by x plus 1, plus a constant divided by x minus 5. So that's what we've got. Now we need to solve for a, b, c, and d all at once. And somebody might be like, well, I mean, this is one equation. We should only have to be able to we should be only able to find one unknown from one equation. All right, fair point. However, we're not just going to worry about having one data point. We do only have one equation. We have multiple data points. We'll get into it in just a second. So here, x squared plus 3x plus 5, multiply by x plus 1, multiply by x minus 5. Right, let's just multiply the whole thing by that. So, what do we end up getting? Well, we've got ax plus b divided by x squared plus 3x plus 5, multiply by x squared plus 3x plus 5. Just going to divide out the bottom. Times x minus 5 times x minus 1. That's my head. No, we're not close. Never mind. Okay. Plus c divided by x plus 1. Multiply by x squared plus 3x plus 5 times x plus 1 times x minus 5. X plus 1 is divided out in both of those cases. Plus d divided by x minus 5 times x squared plus 3x plus 5 times x plus 1 times x minus 5. Our x minus 5s go away in both of those cases. Is equal to, well, we've got all this stuff down here. We've got all that stuff that's being multiplied across all of the tops. So all of it's gone. It's just 1. If you do need to write it out, of course, just for your own edification. Yeah, wait. Then we do have x squared plus 3x plus 5 multiplied by x plus 1 multiplied by x minus 5 divided by x squared plus 3x plus 5 times x plus 1 times x minus 5. Right, so it's all multiplied together. You just get 1 at the end of it. So, oops. Cool. Okay, so starting with the first one, we have here, oops, that is an x plus 1. Right. So what we have here is we have our original x squared minus 4x minus 5 multiplied by our ax plus b. So here we can individually do it just by reckoning. So like, you know, just think about it and see what you get. Alternatively, you could do the table method where you say, look, I'm not going to keep track of all this stuff. Let's organize. We've got a plus ax and a plus b, and we're multiplying it by an x squared, a negative 4x, and a negative 5, and then we draw our lines in. Good evening and welcome everybody from Zach's channel. How are you? E to the 2i pi. It's Zach, everybody. I hope you all are having a wonderful evening. There it is. Hey Zach, how you doing? What was tonight? I did see some math. Didn't stick around quite long enough to discern exactly what topic it was, but We're working on some GRE again. This is Calc 1 for anybody who does not know all of your Calc 1 material. We're working on the method of partial fractions. So in order to split, actually technically I think this is in Calc 2 for us, but you know, everybody does their own thing. We're saying if you have an integral that looks like this thing right here, dx divided by an unsimplifiable, unfactorable quadratic multiplied by a factorable quadratic, here's how we're going to do it. We're going to split it up into these three parts. Our individual factors are all dividing into a constant, and our quadratic needs to divide into potentially a linear function. It can go up to degree 1. If it were degree 2, we could continue dividing it. And if it were, any other higher degree, we could keep dividing that quadratic into that other polynomial. So a linear function is the largest possible function that we can have as the remainder in the numerator. You were just talking about it. Yeah, nice. Didn't have another clap. That's all right. So we were just looking at this one, and I said, if we're going to multiply our original factorable quadratic right here by this ax plus b, some people might find it a little bit hard to keep track of. So one of the options to organize stuff is to do table method like this. I really like it because it's visual. It keeps everything pretty well organized, and I don't think that too many people are going to mess this up. Which I know, challenge accepted, hold my coffee, but nonetheless. Minus 4bx and minus 5b. I also need to write a happy retirement message to one of my colleagues from the community college back in Maryland who is retiring at the end of this year. She was like the first person that I knew in the math department. The first boss that I had there, which granted, not like super serious. She was just kind of like the, she was the coordinator for this particular course. She was the person who came in and did all of the observations for me, like once every 2 or 3 years. And then when I was an adjunct, I was probably thinking about applying for an adjunct promotion until the position, the full-time position, came available. So I applied for that instead. Rest is history, as they say. So I'm trying to mentally prepare myself to write all of that down and say how wonderful it was to have her as, you know, my boss, my mentor, my confidant, my whatever else that we had going on there. She was super energetic and always had stories about her, eventually grandkids, but stories about her kids that morphed into stories about her grandkids once she had them. Okay, so here we've got ax cubed. Here with x squared, we've got two different terms. So we have a plus parentheses b minus 4a times x squared. With the x's, we've got a minus 4b minus 5a. That's going to really tick somebody off being backwards. I'm here for it. Minus 5b. All right, Second group. Similar kind of deal. So x squared plus 3x plus 5, x minus 5. So here we've got an x cubed. Here we've got a negative 5x squared. Here we've got a negative 15x, a negative 25, and a positive 3x squared, and a positive 5x. Alright, and all of those are going to be multiplied by c. So, we have a plus cx cubed. Plus, nope, that's a minus. That is going to be 3 minus 5 is negative 2 cx squared. A negative 10x and a minus 10cx and minus 25c. Here, this is a lot less work because both of the coefficients are 1. So this is going to be an x cubed, this is going to be an x squared, this is going to be a 3x, and this is going to be a plus 5 just along the bottom. Super easy. Along the top, not much harder. 3x squared and plus 5x. Those are all times d. So, a plus dx cubed plus 4d x squared plus 8dx plus 5d. Okay, is equal to 1. Okay, so now we need to reorganize, get everything in terms of each of the individual degrees of the polynomial. So we have on the x cubed term, we have an a, we have a c, we have a d, and the other side was a 0. So there aren't any d's on the right-hand side at all. So all of this stuff is multiplied by x cubed. Excuse me one second. Just going to switch that right there. Cool. Right, both of the sides here, technically, are multiplied by x cubed. That's our label. So all we really need to acknowledge is that x cubed is our label going across, and then we can make the equation a plus c plus d equals 0. And we can eliminate the label x cubed because we know that both sides need to have that stuff. Okay, for x squared, we have a negative 4a, a plus b, x squared, we have a negative 2c, and a 4d. And on the other side, we have no x squareds. Okay, x's. On the left, we have a negative 5a minus 4b. We have a negative 10c, and we have an 8d. And on the right, again, it's a 0. For the constants, we have a negative 5b, a negative 25c, a 5d, and on the right hand side it's equal to 1. Right. So now, and because this is an example that I made up off the top of my head, this is going to get nasty. The good news is that all of these values, A, B, C, and D, are going to be rational numbers. So they will not be, they will not necessarily be integers, but good news is they won't be radicals. So we don't have to worry about that at least. Now, we could go and start pairing things off and plugging things in and whatnot, but why bother? This is what linear algebra is for. So what we're going to do here is we're going to say that this converts into a matrix of A's, B's, C's, and D's, and which equation it belongs to. So we have a 1A, 0B, 1C, 1D in our first row, a negative 4A, a plus 1B, a negative 2C, and a plus 4D, a negative 5A, a negative 4B, a negative 10C, a plus 8D, and a 0A, negative 5B, negative 25C, and 5D. This is the coefficient matrix of the equation, which we can multiply by a vector, A, B, C, D, to get those equations that we just had. There, I guess, right? Close enough. There, I guess. So if we multiplied A, B, C, D by each of those elements in the rows here, then we would end up getting exactly what we had on the left. This is then equal to the stuff that was on the right-hand side, so 0, 0, 0, 1. Then we can make an augmented matrix, which shaves off the important information and drops out our vector. So rather than worrying about that, we just go 1, 0, 1, 1, negative 4, 1, negative 2, 4, negative 5, negative 4, negative 10, 8, 0, negative 5, negative 25, 5, augmented with, so we put a just vertical line, 0, 0, 0, 1. And now what we do is we look at this in terms of performing row operations. So this is all the same stuff that we did in pre-calculus, algebra 2, going back to like high school. All we're really doing here is we're saying that I would like to take linear combinations of each of those rows, each of those equations, right? Take a linear combination of each of those equations and then add them together. So, what we'd like to do is I'm going to stick with having a 1 in the first position here. Our ultimate goal, right, is really to get a matrix that looks like this. Whatever those values are, lowercase a, b, c, d, they will be equal to just what's on the left-hand side there. Oh, look, it's a 1, capital A is equal to lowercase a. 1 capital B is equal to lowercase b. Whatever those numbers are going to be. And again, they have to be rational numbers. So here, having our 1 in the top left corner is awesome. What that means is that we can take 4 times row 1, add it to row 2, and put that result back into row 2. This will then get a 0 in that first position in the second row. Similarly, if we do 5 row 1 plus row 3, and put that back into row 3, that's going to clear another bit. Also, I would actually like to take row 4, multiply it by negative 1/5, and put it back into row 4. What's that going to do? Well, we get 1, 0, 1, 1, 0. Okay, not really surprising there. Okay, so we get 4 row 1, which is 4 in the first position, plus row 2, which is negative 4, put into row 2 is a 0. 4 row 1 is still 0 in the second column, plus row 2 gets us 1. Third column, 4 row 1 is going to be 4 times 1 is 4, plus row 2 is a negative 2, so we drop and we get 2 left over. 4 row 1 is 4 at the top, plus row 2 is another 4, so that's going to be 8. And then our right-hand side is all zeros, or both zeros for rows 1 and 2. So any linear combination of zeros is 0, right? Pretty obvious there. Additionally, I'm just going to put in the bottom. So we get a 0, a 1, a 5, and a negative 1, with a negative 1/5 as the constant at the bottom. Having a fraction is slightly inconvenient, but we'll put it low on our priority list. We will try not to use the negative 1/5 as like a driver for any of the other stuff above it, as much as we can. Okay, row 3. So we want 5 times row 1, which is 5, plus row 3, which is negative 5. So that's a 0. 5 times 0 in column 2 is going to be 0, plus row 3 is going to be a negative 4. Okay. 5 times row 1 is going to be 5 in column 3, plus a negative 10 is going to be a negative 5. 5 times row 1 is 5 again in column 4, and then plus the 8 from row 3, and we get a 13. And again, zeros on the other side. It would not surprise me in the least if at least one of these things were 0 itself. I guess it would have to be either exactly 1 or all 3 of them. Oh, it can't be all 3 because the bottom one is negative 1/5. So 2 of them have to cancel out, and the third one is going to be... Nope, that's not how that works. At the bottom, either all 3 of them just add to negative 1/5, or 2 of them cancel each other out, and the last one is negative 1/5. So we'll see how that goes. Okay, so we leave rows 1 and 2 where they are. Row 3, we're going to add 4 row 2 plus row 3 put back into row 3, and a negative row 2 plus row 4 put back into row 4. Once you get practice to this stuff, it's a lot faster. Also, if you're allowed to, this has a special name in linear algebra. The form that we want is called row reduced echelon form, or RREF. There is a calculator function that you can just like plug that in. You do need to know what you're doing though, so do be careful. Right, row 2 stays the same. Row 3, we have 4, row 2 is 4, plus negative 4 is 0. 4 times row 2 is 8, plus a negative 5 is going to be a 3. And 4 times, oh dear, 4 times row 2 is going to be 32, plus 13 is going to be a 45. And 0. Okay, this is still a 0. And again, negative row 2 plus row 4 is a 0 here. Negative row 2 is a negative 2 plus row 4 is a 5, so we get 3 total. Negative row 2 is negative 8 plus row 4 is negative 1, so it's negative 9. And the other one is a 0. Row 4 stays as is. That's a negative 1/5. Interesting. Cool. Row 3 times a 1/3 is going to go back into row 3. Row 4 times a 1/3 is going back into row 4. Right. So this is where it gets a little more challenging.
On January 2nd, over 300 people were seriously ill with flu in our local hospitals.
No, don't do that. Right, row 4, we want to get rid of the 3 that's in row 4. So we can do a row 3 minus row 4 put into row 4. It's way better. So 1, 0, 1, 1. Leave those as is. Nothing there is going to change. These are all multiplications, so that's not going to change that either. So 0, 1, 2, 8. And then a 0, 0, 1, 15. Last one, 0, 0, 0, because here we take a 3 minus 3 on the stuff above, right, up here. 3 minus 3 gets us a 0. And then 45 minus negative 9 is going to be a 54. This is gross, but you know what? It's going to work. And then row 3 is 0 minus negative 1/5 is going to be a positive 1/5. And I told you all that this was going to be pretty nasty because I made it up off the top of my head. You might have thought I was kidding. Generally speaking, that's what happens. We take row 4, multiply it by 1/54th, and put it back in row 4. Okay. Row 1. Take row 1, subtract row 3, put back into row 1. It's going to clean up some of the stuff that's there. I'm not going to work with 54ths and 15ths and 8ths, so we'll just do one thing at a time. Row 2 minus 2 row 3, put back into row 2, and leave row 3 for one more round. As much as it would not be that much of a hassle to do 15 54ths simplified, I just don't want to. Perfectly valid reason. Oops, nope. Row 1 minus row 3. So 1, 0. All are subtracting zeros at the bottom. And then we have a 1 minus a 1 is a 0. And a 1 minus a 15 is going to be negative 14. And row 1, row 3, both zeros on the right-hand side. 0, 1. Row 2 is going to be a 2 here. Minus twice row 3 is going to be minus a 2, so we get a 0. Okay, we have an 8. And we subtract twice 15 is 30, so that's going to be a negative 22 with a 0. All right, 0, 0, 1, 15, 0. And last one here, 0, 0, 0, 1. And 54 times 5 is going to be 270. Yes. 1 over. 1 over 270. Right? Now we know how much everything's worth. So, we could just translate this back into equations. We could finish this out in terms of row reduced echelon form. Porque no los dos, right? This is going to be A is equal to 14D. B is equal to 22D. C is equal to negative 15D. And D is equal to 1 over 270. So, equations-wise, works out pretty nicely. Just pop those over 270 and simplify. So, A is equal to 14 over 270, which is going to then be, do we divide by 7? Probably not. No. Divide by 2. So 7 over 135. B is equal to 22 over 270, not divisible by 11, but divisible by 2 is going to be 11 over 135 as well. C is equal to negative 15 over 270. This one's a little bit harder because we have multiples of 5 and 3. So we can divide 270 by 15. If we go back up to here, we could say if we divide by 5 and we divide by 3, we're left with 18. So this is going to be a negative 1/18. And then D is equal to 1/270th. So none of them are 0 this time around. Cool. Okay. Let's actually move this because I wasn't thinking ahead. Okay, this is going to be row 1 plus 14, row 4, put back into row 1. This is going to be row 2 plus 22, row 4, put back into row 2. This is going to be row 3 minus 15, row 4, put back into row 3, and row 4 is already done. So, hooray. 1, 0, 0, 0. 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. Augmented. Again, this is going to be a plus 14 over 270. Divide both by 2, we got 7 over 135. Second row was 22 over 270 is 11 over 135. Negative 15 over 270 was 1/18th. And 1 over 270 for the last one. Okay. Those are our constants. Let's copy that. And then move back up to here somewhere. Here. Paste. It works so well. Okay. So, we could separate all these out individually, and this would make the first one. 1 over 135 is a constant that we can just send out. This is going to get us a 7x plus 11 over x squared plus 3x plus 5 dx. Plus, and in fact minus, 1/18th integral of 1 over x plus 1 dx. Plus 1 over 270 integral of, yes, 1 over x minus 5 dx. Well, I don't know about you, but that looks a lot more manageable. Okay. So, what we're going to have now is a few different pieces that don't quite work as they sit. So, first of all, these two here and here, logarithms. Right? These are logarithmic integration, no problem. So, or integration of what becomes logarithms, I don't know, however you want to say it. These are super simple. We just get natural logs. It's all good. This one, on the other hand, right? If we do a u substitution, then what we're going to end up with is u is going to be equal to x squared plus 3x plus 5, and du is going to be equal to 2x plus 3 dx. Yeah, we can make it do that, but it's also not going to work entirely nicely. So we could work out some constants to make at least part of it work. But even that, right? 7 and 11 are not off by a factor of 2 to 3. That's just, facts of life here. We're not going to be able to get those numbers super nicely. However, we will be able to get at least some of the stuff to work out okay. And we can make a workaround. Right, this is going to have a ratio of 2 to 3 between these two terms. Again, 7 and 11 do not match. So what do we do with it? Well, what I would want to do is say, okay, we've got 1 over 135. We've got the integral. Now, what we want is to make it work in a way that's going to be at least somewhat reasonable. I'm going to make sure that our 7, the number out front there, the leading coefficient, is going to have both of those terms in it, a 2 and a 3, so that when we shift stuff around a little bit, I don't have to get fractions. Right? We could do fractions, that's not a big deal. But if you think a little bit deeper beyond what is strictly necessary, there is something that is convenient. So if we multiply that whole term by 6, we get 42x plus 66. And then we have to divide by 6 somewhere. So multiply by 1/6 on the outside as well. You get x squared plus 3x plus 5. Now, why on earth would you do that, Obi? That's just making things unnecessarily complicated. Well, sure, fine. You can do it the way you want to do it. And I'm just going to say that in this particular step, we can now get a ratio of 2 to 3 out of our 42x and a constant. It's not going to be 66, right? Because that's not a ratio of 2 to 3. But rather, what we do have is 42x plus 63 is a ratio of 2 to 3. And then we've got 3 left over. And then what we can do is separate into 2 separate integrals. Say that what we've got here is going to be 1 over 6, 7, 88, 10. Is 27 times 3 is 81. Yeah, cool. Okay. So we've got this dx, we've got this dx. X squared plus 3x plus 5. And then again, in the second one, we've just got this 3 that's here. Still x squared plus 3x plus 5 in the denominator. It's still unfactorable. You can't do anything with it. So we're going to have to find another workaround for that term. However, the first term is now a u substitution. What we've got is an integral with a 21 factor between both parts. And that leaves us with 2x plus 3 over x squared plus 3x plus 5. If you remember, dx. This is right here, right? This is the u substitution we were looking for up here. du is equal to 2x plus 3 dx. Look, now we've got it. It's explicitly the same. So this is going to end up being, again, 21 times the integral of du over u. What do you know? It's another logarithm. This is still 1 over 810. And then this next term, this is where it's going to get slightly tricky, yet again. Negative 1/18 integral dx over x plus 1 plus 1 over 270 integral dx over x minus 5. What we have here is an inability to get any of the u substitution stuff. However, we can do completing the square, because if you remember, we can split this up into something squared plus something squared, or minus something squared, because we did that for our trig stuff before. So now we can do one of these trig things. And we say that completing the square is going to end up being dx over x squared plus here. This is going to be 3 over 2, and then we square that is going to be 9 over 4. Remember, this is x squared plus 2x plus 1, something of this form. All right, ads are about to start. We'll be back in just a few minutes, and we'll finish this up and then move on to definite integration. See you all in 3.
My toes are killing me. These shoes feel so tight.
Still wearing those pointy things?
I mean, aren't all running shoes like this?
Nope, you need Ultra.
Ultra?
Their shoes are shaped like your feet with a roomy toe box. Way more comfort. You crush your run, not your toes.
Okay, that sounds dreamy.
Balance, strength, comfort. All from the fit. Ultra just gets it. Ultra, stay out there.
When regular painkillers alone just don't cut it. Neuromol dual-action pain relief tablets contain the power of ibuprofen
and the strength of paracetamol,
combined together to provide faster, longer-lasting, more effective relief than regular painkillers alone. Hit pain hard
with Neuromol dual-action pain relief. Neuromol dual-action pain relief tablets for pain relief not relieved by the regular painkillers ibuprofen or paracetamol individually. Always read the label.
The year is 1991. Birds and people are living together in seemingly perfect harmony. Until one day, a young man catches fire. This is Phoenix.
All right, welcome back in. So, if you remember, we were essentially trying to do like this. Maybe A is a terrible idea. M. Right, x plus m squared is going to get us x squared plus 2m plus m squared. So, if we know that 2m is 3, 2mx. If we know that 2m is 3, then m is going to be 3 over 2. And then when we square it, we end up getting 9/4. So this is going to be x squared plus 3x plus 9/4 plus the rest of it to get us up to 5. So 5 in fourths is going to be 20/4. We just took 9 of them, so that leaves 11/4 left over. These are going to be grouped, and then we're going to take them, and you know what, let's not even waste time copying this stuff right here. We could just move it right on over. Woohoo! Okay. So now we have this plus integral 3dx over the first bit is going to be x plus 3/2 squared plus 11/4. 11/4 is also back up. The square root of 11 over 2 squared. Okay. Now, this one is going to be 21 over 810. So if we divide by 3, that's going to leave 270 on the bottom again. So 7 over 270. Times. This is du over u. We take the integral that's the natural log of the absolute value of u plus c, but we're going to chuck all of the plus c's all the way at the end. So this is absolute value of u. U is that quadratic that we had up there that was unfactorable. We'll come back to that in a minute, or we'll recopy it on the next line. Plus 3 over 810 is going to be 1 over 270. Then, the integral of, all right, this thing, so, that appears to be, right, the hypotenuse of this particular right triangle squared. So if we went with theta here, those are the two legs. It doesn't really matter which way we go with this, again, as usual. Right, so this is effectively what we've got here. It's pretty gross. But effectively what we have is that we have a constant divided by the hypotenuse squared. Right, so this one is going to end up being our adjacent leg here. It's not going to be the one with the x, right, the opposite side. So that's just going to be adjacent. So we could make this the adjacent over hypotenuse and like parentheses squared, or it is the square of adjacent over hypotenuse. So right, take all of this and square it instead of just the denominator. So what is this? This is the cosine squared of theta, but now we have to deal with the fact that we don't have all of the constants in the right places. This also is going to get me to look at this and say, okay, the other option is that let's actually take this and say, alternatively, the tangent of theta is going to be equal to x plus 3/2 over root 11 over 2. Scratch myself. Okay, so alternatively, this is going to be secant squared of theta if we take the derivative of all this. And then this stuff is going to become 2 over root 11 dx. D theta in here. So this is pretty messed up. But essentially what we've got. Right? If we want to move everything around, cosine squared is going to be equal to the root 11 over 2 divided by the square root of all that stuff. X plus 3/2 parentheses squared plus parentheses root 11 over 2 parentheses squared. Okay. So this is going to be 11 over 4 times that x plus 3/2 parentheses squared plus root 11 over 2 parentheses squared. End. So we need an 11/4 to be put in here. We don't have it, so that needs to be a 4/11 multiplied on the outside in order to balance it. Then we also need another dx is going to be equal to that's all right. We'll multiply here by another. Oops. We need 2 over root 11 times dx. In order to get dx to convert completely. We need an 11 over 4 times that thing here. X plus 3/2 parentheses squared plus parentheses root 11 over 2 parentheses squared end parentheses. All of that converts. So this is now going to be a right, and we don't have the 2 over root 11, so we need a root 11 over 2 on the outside in order to balance. So say 1 2/70th natural log absolute value root, absolute value of u. Leave it there for now because we're not going to, I'm not converting that. It's fine. As it stands, right, we could simplify this, make that a 2, make that a 1. Smooth Space Odyssey, or Oddity, good evening and welcome. Welcome back to the channel. How's things? This is one of those, at this point, you shouldn't just make up problems off the top of your head sorts of moments. Yeah, we usually want to use vetted problems so that they're a little bit easier to work with. I went and decided that we were going to do this Calculus 2 level problem. You know, find the integral based on this particular setup, 2 quadratics multiplied together in the denominator of a fraction. Not actually a big deal. Needed to use partial fractions in order to get it. Did that. And then we needed to break up the 3 things that we had into 4 separate integrals. Did that. And then now we've just basically been doing bookkeeping to make sure that all of the parts are where they need to be. This is going to be a 1 over root 11 over. This is a 2970 divided by 2. Okay, so 14. Yeah, 85. 1485. Writing a paper. Nice. May I ask what it's about, or is that rude? Okay, with this part, because all that stuff ended up working out properly, this now ends up getting us a secant squared theta d theta in the numerator. And actually, right, and the whole fraction itself is the cosine squared of theta. So this actually works out super nicely because secant times cosine is 1. So these two things end up dividing each other out, and we're just left with 1 d theta. At one point, I had a lot of students who probably would have complained about that and been like, this is such a waste of our time if that's all you get. But the point is that because we arranged everything in just such a way, a lot of the other extra stuff that's there just kind of collapses, disappears on us. And that's a good thing, because you don't really want to deal with it with all the extra little bits. Sometimes you literally can't do it. Oops. Alright, natural log absolute value x plus 1 times a negative 1/18th plus a 1 2/70th times the natural log of the absolute value of x minus 5. Okay. Ooh. Minus 1/18th natural log absolute value x plus reinterprets co-area formula geometrically and probabilistically, treats level sets as inducing a control measure that minimizes variance in Monte Carlo integration, essentially geometric form of Rao equalization, connects differential geometry, measure theory, probabilistic control through geometry of level sets. Whoa. As you could probably tell, I didn't get that far. Alright, 1/270th times the natural log absolute value of x squared plus 3x plus 5 root 11 over 1485 times the integral of d theta, which is theta. Theta is also just equal to the arc tangent of the bit on the right, that fraction. So we can eliminate theta here and say, ah, this is an arc tangent of that fraction. I'm going to multiply both top and bottom by 2. So this gets us a 2x plus 3 over root 11. I don't care. Right? I don't care about rationalization of denominators. It's nonsense unless you absolutely need to do it. Nah, don't worry about it. There is the possibility that somebody will come along and be like, oh my god, I've been looking for somebody doing that. So, never know. Minus 1/18th natural log absolute value x plus 1 plus 1/270th natural log absolute value x minus 5. Alright, that's it. So, it is really big and nasty and ugly and all that. However, right? However, this is doable now. So it used to be that we'd go up and we'd see an integration like this and we'd look at it and go, yeah, I can't do that because there's no u substitution, or there's no, particular integration that I know that has a product of two quadratics in the denominator, or even just the product of two things in the denominator. Like, none of those patterns have worked. So what do we do with it? Well, now we've got partial fraction decomposition, where we can take any products of things and then turn it into the sums of things. So, as we said here, as long as you factorize it down as low as you can, it's also equal to this sum here. And remember, all of our degrees in the denominator are going to indicate the, if you subtract 1 from that degree, that's the largest degree object that you can put in the numerator without it also dividing, without the thing in the denominator dividing the thing in the numerator. If it is, like, of the same degree or a higher degree on top, then, yeah, you need to keep working at your division. Right, we did some matrix algebra to figure out what these were. Again, this is all by hand, so, yeah, it took us, like, an hour and 20 minutes to do this, but we took a break. We were talking about a bunch of stuff, and we're showing how to do things. The next one that we do, I'll find an example that's a bit better, and we won't really do that much instruction on it. It'll just be running through. right? And in theory, you can collapse some of this natural log stuff into a single natural log. I don't recommend it. Most people will also agree that that's kind of pointless. Like, don't do that to yourself. It's nicer just as it is. And you can see all the individual natural logs. In addition, when we get to this in differential equations, because you need to do this in differential equations, it makes it a bit nicer to work with when all of them are separate natural logs. If there's a bit of algebra that also needs to be done. Okay, let's... Calculus Volume 2. View online. No, just go to the book. And partial fractions. Let's do one that's actually like an example in the book. So we want to evaluate the integral of x minus 2 divided by, parentheses, 2x minus 1 squared times x minus 1 dx. Alright, and now we can close that. Well, don't close the book, just... Okay, so for this, we want to do the same thing. We want to say that, you know, asterisk over here on the side, we need to get x minus 2 over, parentheses, 2x minus 1 squared times x minus 1 to be equal to the sum of the fractions 2x minus 1 parentheses squared and in the denominator x minus 1. Right, so here you might say, oh, well, this is a quadratic, so we need a linear up top, so this is going to be ax plus b. And then over on the next one, we've got just regular constant over x minus 1. Okay, this can work. However, this ends up collapsing a little bit, and what we can do is instead write this as a constant over 2x minus 1, because we need to capture a 2x minus 1 as like a single factor, plus a b over parentheses 2x minus 1 squared. And then plus c over x minus 1. Basically, the better way to deal with it is to just say, okay, we're going to use 2x minus 1 as a linear and also a quadratic factor, and then just use a constant for every instance of that term, 2x minus 1 in the denominator. It's kind of up to you how you want to do it, because you could have that be ax plus b over parentheses 2x minus 1 squared. And actually, why not, let's show it both ways. I'll do the one that is recommended first. So x minus 2 over parentheses 2x minus 1 parentheses squared times x minus 1 is equal to all that stuff. And again, linear factor, quadratic factor, the exact same denominators, and then they're both just constants a and b, respectively. If we multiply both sides by 2x minus 1 parentheses squared times x minus 1, then we end up with x minus 2 on the left. And on the right, we've got a times 2x minus 1 times x minus 1 plus b times 2x minus 1 parentheses squared is now all eliminated, and we just get x minus 1. Plus c times x minus 1 is gone, and you're left with both factors 2x minus 1 squared. So x minus 2 is equal to, here, when we multiply this out, we're going to end up with a 2x squared. Negative 2 minus 1 is a minus 3x plus 1. And then all of those need a's. So 2a x squared minus 3ax plus a plus bx minus b plus 4cx squared. Minus 2 is going to be a minus 4cx plus 1c. All right. So for this, now the right-hand side becomes, what do we have for x squareds? We have a 2a plus 4c x squared. Oops, x squared. We need those for a minute. Okay, plus parentheses, negative 3ax plus bx minus 4cx. Factor out the x. And then the constant, we get a plus a minus b plus c. This is all equal to x minus 2. So this means that 2a plus 4c should be equal to 0 because there are 0 x squareds on the left. Right, so our x squared line is that. Our x line is negative 3a plus b minus 4c is equal to 1, because we have 1x on the left-hand side. And then constant, we have a minus b plus c is equal to negative 2. Okay. So then we need to use these again, linear algebra, find out what the actual values are for a, b, and c. So here we can actually make this a divide by 2, so we get a plus 2c is equal to 0. Doesn't change much, but, you know, makes it look a little bit nicer. So 1, 0, 2, augmented 0. Next line, negative 3, 1, negative 4, augmented 1, and 1, negative 1, 1, augmented with negative 2. Okay. This is going to be row 3 minus row 1 to get rid of the first number. This is going to be 3 row 1 plus row 2, no, not equals, put back into row 2, and then leave the first one as is. Works well enough already. 1, 0, 2, 0. 3 row 1 is 3, plus a negative 3 is going to be 0. Next one, 3 row 1 is still 0, plus row 2 is 1. 3 row 1 in the third column is going to be 6, plus row 2 is negative 4, makes a 2. And then this was just row 2 in the constant, or on the right hand side. Right, our row 1 is 0, so none of it changes. At the bottom, we get row 3 minus row 1. So this is a row 3 is at the bottom, minus row 1 at the top is 1 minus 1 is 0. Next one here is going to be a negative 1 minus 0 is a negative 1. Row 3, 1 minus row 2 is going to get us also a negative 1. And this is row 3 is a negative 2 minus row 1 is 0, so you still get negative 2. Okay, I'm going to take row 2 plus row 3, put back into row 3. I was thinking about, like, multiplying it by negative 1 and doing stuff, but you don't need to, right? We're trying to get rid of this term anyway, so might as well get rid of it. 102 augmented 0. 0, 1, 2, 1. 0, 0. Row 2 plus row 3 is going to be a 1. And row 2 plus row 3 is going to be negative 1. So now we get row 1 minus 2 row 3. Row 2 minus 2 row 3. And then keep. So we end up with 1, 0, 0, augmented with. Negative 2 third row is going to be a positive 2 total. And 0, 1, 0. Row 2 minus twice row 3 is going to be 1 minus negative 2. It's going to be a positive 3. And 0, 0, 1, negative 1. Okay, so here A equals 2, B equals 3, C equals negative 1. Oops. Okay, so one more time. This is going to be 2 over 2x minus 1 plus 3 over 2x minus 1 squared minus 1 over x minus 1 is equal to x minus 2 over 2x minus 1 parentheses squared times x minus 1. Okay, so we don't even need the right-hand side, really. That's just more or less, showing that this is actually equal to that. And then this can now be integrated. So what is the integral of 2 over 2x minus 1 dx plus integral 3 over parentheses 2x minus 1 squared dx minus integral of 1 over x minus 1 dx. Well, the first one, yet again, is a u substitution, and it's in logarithmic form. So u is equal to 2x minus 1, du is equal to 2 dx. So we've got 2 dx on the top, we've got a 2x minus 1 at the bottom. This is just the integral of du over u, which we know is the natural log of the absolute value of u. So here, natural log absolute value 2x minus 1. Last one, same deal. This is a minus natural log absolute value x minus 1. The middle stuff is ever so slightly harder. It's not really, but you know. Here, what we've got is if we let u be equal to, again, we could just do the same as before. So use the same u and du here as well. We need, right, this is going to be the integral of du over u squared. So this ends up just being a regular power rule, or u to the negative 2 du. It's all the same stuff, really. The thing that's going to be different in this case is we're going to need an extra 2 to be a part of our du. So 2 dx is necessary. So that means we need another 1/2 on the outside. So this is going to be a 3/2. We didn't use that 3 anywhere. So it's just going to get kicked out front. Then when we take the integral of u to the negative second, the new power becomes, gets divided into the other numbers that are there. So negative 3 over 2, and then this is going to be u to the negative first. So what does that mean? Well, we could take that out and make it just parentheses 2x minus 1 to the negative first. Oh, whoops. I forgot. Mark me off a point. Plus C. I know most of you probably lose a point if you forget it. Okay. Right, since there are no constant multiples out in front of the natural logs, with the exception of the -1, that's just going to determine where this is. So this is going to be like absolute value of 2x minus 1 over x minus 1. So we can do that. Then we'd also get a minus 3/2 or a minus 3 over 2 parentheses 2x minus 1. Or 4x minus 2, or whatever else you feel like doing. Plus C. Okay, so what about the other way? What happens if we let that be a linear factor over the quadratic and then do plus c over x minus 1? So in this particular case, all it needs to be is equivalent for us to just look at it and say, yeah, it'll work fine. So here, we're going to take x minus 2. We're going to multiply both sides by our denominators. This is going to get us our ax plus b times x minus 1. And our c multiplied by 2x minus 1 parentheses squared. So we got x minus 2 is equal to, here we've got an ax squared plus bx minus a, so negative a plus b, parentheses x minus b. Plus c times, this is going to be, again, 2x parentheses squared is going to be 4c x squared. Here we've got a negative 1 and a positive 2, so it's going to be a negative 2 and again negative 2 from the square bit. So negative 4cx and then plus c times 1 is our constant. So our square equation is going to be that a plus 4c has got to be equal to 0 because there are no x squareds on the left-hand side. X is going to be a negative a plus b minus 4c equal to the 1 from the left-hand side, so 1x. And then constant. I will say these are going to be different numbers explicitly, but it's going to shift ever so slightly, and then we're going to be able to see, oh, what do you know? It's all the same stuff. Should have used different letters, I guess, than A, B, and C, but you know what? It's fine. Okay, so our constants are going to be negative b plus c is equal to negative 2. And then again, do linear algebra. So we've got a 104 augment 0. Negative 1, hey famished, how's it going? 1, negative 4, 1. Oh, that one's so simple. Look at that. Look at that. Do you see it? Do you see it? Because I didn't see it up here. As silly as that is, that I didn't see it up there. It's bright as day down in this area. And then a 0, negative 1, 1, and negative 2. You see it yet? Row 1 plus row 2. Put back in row 2. Oh, so nice. Right. So this is going to get us a 1, 0, 4 augment 0. This is going to get us a 0, right? Row 1 plus row 2, 1. 4 plus negative 4, 0. 0 plus 1, 1.
My toes are killing me. These shoes feel so
Okay.
tight.
0, negative 1, 1, negative 2. Now we can take this and say, okay, take row 2, add row 3, put it back into row 3. And that's going to work for us. Then 104 augment 0. 0, 1, 0, 1. 0. 1 plus negative 1 is 0. 0 plus 1 is 1. 1 plus -2 is -1. And then this is going to be take row 1, subtract 4 row 3, put it back into row 1. 1, 0, 0. Row 1 is 0 in the constants. Minus 4 times -1 is going to be a positive 4. 0, 1, 0, 1, 0, 0, 1, -1. So A is 4, B is 1, C is -1. Again, these are different numbers, somewhat, so it is a little bit weird. Okay, so this is going to be 4x plus 1 over parentheses 2x minus 1 squared plus minus right, 1 over what was the other one? X minus 1? Yeah. Alright, so what does that do for us? Well, this says that here, if we divide our 2x minus 1 into the 4x plus 1 that's above, right? That's going to be a 2. However, we're going to then have extras. So if we do literally, right, 4 and a 1 and a 1/2 as our number here, we get a 4, 2, 3. And then we need to multiply by 2 when we're done. Not important. Right, how do we express that algebraically? So we're going to say that this is going to break into 4x minus 2, but it's got to still be plus 1. So minus 2 plus 3 ends up with the balanced amount. When we divide by 2x minus 1, squared. Yeah. Right, it's all squared. Minus 1 over x minus 1. That's less important right now. Here, this is 2 times 2x minus 1. So now this is a 2 divided by 2x minus 1 plus 3 over parentheses 2x minus 1 squared minus 1 over x minus 1. That should be the same thing as what we got down here. Somewhere. Yeah, so 2 over 2x minus 1 plus 3 over 2x minus 1 parentheses squared minus 1 over x minus 1. Same thing? Yep. Why do we do it that way? It's all the same stuff. So you could choose to do it one way or the other, as long as you're explaining your work and how it's supposed to go through, then yeah, that'll work. yeah, we can go another 40 minutes or so. Let me know if anybody has any questions, what sorts of things you might be interested in looking at after this ad break. There you go. Jeez. My clock was like, I don't know, 40 seconds off. This is weird. So, like I said, we're going to take a 3-minute ad break. Thanks so much, everybody, for coming. And we'll get into the last section, which is going to be on definite integration and Riemann sums. So, see you in 3. Get some more water, stretch, do what you need to, and be right back.
Did you know Tesco Bank does credit cards? And they're the only credit cards around that get you extra club card points. With a range of credit cards to choose from at 24.9% APR representative variable, you could find one that's right for you. If you didn't know we do credit cards, you do now. Search Tesco Bank credit cards to learn more today. UK residents aged 18 and over, subject to status, minimum spend applies when collecting points. Tesco Stores Limited acts as a credit broker. Barclays is the lender.
I did just remember there is another way that some people have liked doing partial fractions, which is that when they get down to the when they get down to this step, they do like just plugging in values, which is mostly fine, I guess. So when x is equal to 1, right? If x is equal to 1, then we get a 0 for this value here, which is going to wipe this entire thing out. Over here, we're going to get c times. This is going to be 2 times 1 minus 1 is 1. Squared is still 1. And then on the other side, we get a 1 minus 2 is negative 1. So c is equal to negative 1. What do you know? And then we look at this again and we say, okay, take this one over here, and you say that if x is equal to a half, then it wipes this one out. And then we have a half minus 1 is going to be negative a half. And then over here, a half minus 2 is going to be negative 3 halves. Multiply it by 2 going across, so you've got some balance between the left and the right hand side. And then x, right, is still a half here. So a half a plus b is equal to whatever we got there. And then, since this is the issue, is that you can't really go anywhere else from here because there aren't any other zeros for this particular function. So you're either just going to have to pick a number and then deal with the consequences. You know, negative 1, positive 2 actually could wipe out the left-hand side entirely. So 2 is another option. And then it allows you to, yeah, it allows you to solve for a different value, or using different values. It's okay. I don't prefer it just because I'm not going to complain if somebody does use it to find the answer. That's fine. But if somebody's using that as like, this is the only way to do it, absolutely not. I prefer that students would learn the linear algebra because, oh, look at that, we're solving systems of equations. It's the same stuff you've been doing since Algebra 2, it's just in a new way. So we're using linear algebra in order to figure all that stuff out. But again, overall, it doesn't matter. It doesn't matter which particular method you're using. So, it's all good. All right. So when we're talking definite integration, we'd introduced the concept a while ago that integration was area under a curve. We did kind of state it very briefly because we weren't really using areas under specific curves. That's the job for definite integration. When we were doing indefinite integration,
Dim sum for breakfast? Oh, sign me up. I'd be in Rome, submerged in flour, learning to make real pizza.
Travel far from where you are. Flying from Leeds Bradford Airport via
right, this mostly was talking about
Visit klm.co.uk.
finding antiderivatives. So we were saying, okay, when you're looking at taking the derivation of a particular function, indefinite integration is undoing that. So we are trying to undo integration. For definite integration, we're talking about over a specific area, over a specific interval. We would like to find the area that exists underneath the curve. So for this, right, so one of the things we can do is find a bad approximation first, and then try to make it better as our thinking moves along. Right, so one of the examples could be like y is equal to 9 minus x squared on the interval from 0 to 3. Now we're doing this we're doing this because it makes it a nice particular position on a parabola. So we're going from 0, 9 down to 3, 0. It's parabolic. We're trying to find what is the area under this curve. Okay, so how do we find area? Well, if we want to find a bad approximation of this particular thing, we might just say, use the, hang on. Let's take this whole thing and copy it. Again, here, this is our goal, but we can't do that yet. We don't have a particular setup that allows us to do it. Okay, so what we can do is make a very poor approximation by, like, making a box. Right, find the entire area of this rectangle. We have 27 here. No. We have 9 here. We have 3 here. That's 27. There we go. Right? Terrible approximation. But at least it's kind of interesting. It gets us at least better than guessing a number. Okay, what if instead of one box, we made 2? So we start here, and we split this whole thing just in half here. Okay, now, what do we do about the rest of it? Well, we could either throw in a random sort of box, or notice what we're doing for the first box. We're starting at whatever point the function was at, and then it just goes straight over and then straight down. Here, we find where the function has its value at that particular x value. Draw it out, and then draw it down. So for this one, we get an area that's going to be, well, let's see. This is going to be a height of 9 and a width of 1.5. This one is also going to be a width of 1.5. Its height, 1.5 squared, is 2.25, which is going to be 6.75. 6.75. Going up that way. Right, so take this. And we say 9 times 1.5 is 13.5. And 6.75 times 1.5 is going to be 10 something. 10.125 plus 13.5 is going to be 23.625. Okay, then what about here? If we want to get a better approximation still, we can do the same deal where we start with drawing out where the function is going to hit particular x values. What are those x values going to be? Well, we divided this into 2 subsegments, so why not do 4? It's kind of the obvious next choice. Ismail from Brazil, good evening and welcome. My name's Obi-Wan Pez, this is N Simplex Pachinko, and we're doing some Calculus 2, well, okay, we just moved back into Calculus 1 again. We're talking about Riemann sums and definite integration. If you have any particular questions, let me know, and I will be happy to try to answer best I can. Okay. So here, this is also going to be a height of 9. But now our interval side to side is going to be 0.75. Okay, so this means that we need to now find all of the x values, well, we could find all the x values, but find all the function values for each of those individual x values going across. So oftentimes what I do is I go into my y equals menu, hashtag not sponsored TI. This is y equals 9 minus x squared. We go into the table. Nope, okay. Okay, we go into our table, set the table set to independent ask, and then you just type in manually what values you want for your x values. So if we do this, technically, right, we're going to start at 0, 0.75, 1.5, and 2.25. And then the last one is 3, but we don't really need it, right? We don't need the actual value, but it's all right. So we get a 9, then we get 8.4375. $8.4375, a 6.75, and a 3.9375. Those are all multiplied by 0.75 going across as their widths, and then that is going to get us the area of those 4 those 4 rectangles. So then we're going to take, okay, so we want this in the list actually. If you go to stat edit, you get a list. It makes it a little bit better. So clear enter, get rid of all this data, which I don't know actually what it's from or when it's from. Again, 0, 0.75, 1.5, 2.25, and 3. All right, our L2 is going to be equal to 9 minus L1 squared. Cool. It'll auto-populate once you do that. And then we want to go over and say, now what is the area of each of those things? So take L2, multiply each of those values by 0.75, and now we get our areas, which are going to be 6.75, 6.3281, 5.0625, and 2.9531. So we need the sum of L3. Oops. Really? Area is equal to 21.09375. All right. This summation method, right? If we keep going, and I do mean keep going, this summation method will eventually yield the exact result. The problem is that it takes literally forever to get there, because now we start talking about, well, if we want to subdivide, not in halves, not in quarters, not even in eighths or sixteenths, but if we want to subdivide our x interval from 0 to 3 into 1,000,000 partitions, we could do that. It's going to take a while to calculate them, but we can do that. You know what's really good at doing calculations? Does what it says on the tin, right? A calculator is extremely good at finding all those particular calculations and then reporting back. You could also do this on your computer if you have a particular programming language you like. MATLAB, Python, C, C++, etc. They all work. They're all going to allow you to do Riemann sums. These were named after Bernhard Riemann, who was a German mathematician. At that point, maybe it was still Austro-Hungary. Anyway, so Riemann ended up creating this limiting process. So what happens is that if we were to take the limit as n, the number of partitions, starts going off toward infinity, then the things that we're multiplying together here are going to be our heights. So this is going to be our function value at every individual x value, multiplied by the horizontal distance, which is our delta x sub I. Technically, they could be different from each other, so this is why we do delta x sub I, but a lot of places teach it these days where it's just going to be delta x. So you're going to fix your delta x as a set value. Most of the time, it's probably the case, but it doesn't have to be. In addition, that is true for any one partition, but if we want to find all of the partitions, we need to sum them up. So I is going to go from, I guess, 1 up to n.
Tesco Bank does credit cards. And they're the only credit cards around that get you extra card points. With a range of credit cards to choose from at 24.9% APR representative variable, you could find one that's
Right,
right.
so this is going to be
No, we do
the
credit cards. You do now. Search Tesco Bank credit cards to learn more today. UK residents aged 18 and over.
height
subject to
of
status,
each.
no spend applies when collecting points. Tesco Stores Limited acts as a credit broker.
And then
Licensed
here,
lender.
delta x sub I is going to be the width of each. Right, so eventually this is going to start looking like this. Don't get into harmonic wave frequency. Don't tip your whole monitor over. Right? So as n goes to infinity, area is more accurate. Right, to the point of point of exactness at the limit. So for us, what we've got now is we want the sum as I goes from 1 to n of our function 9 minus x squared times our delta x, which the delta x itself can be b minus a over n. So b and a are going to be our ending and starting points, respectively, on the interval over which we're working. So we're going from 0 to 3. This is going to be 3 minus 0. Over n is the number of partitions we're doing. Right, and then those terms there, the 9 minus x squared, all over n. I guess x sub I, right? Right, so here, if we put the limit in, again, all this stuff is going off to infinity. Sorry, n is going off to infinity, and the area is bounded. So that should not be going off to infinity either. Our area here is bounded. So we should reach a particular we should reach a particular value for that area. The book went through the derivation of the thing, going from partial sums to finding the formula of the sum of all, or n number of quadratics. So I was trying to find the impetus as far as where that was going. Oh, okay. Huh. Alright, so that's a look at how we would do Riemann sums. If you want to plug this into the calculator, it's not terribly difficult. Plug it into a programming language of your choice. It's not terribly difficult. Basically, you're going to pass in functions, and then you're going to pass in limits of integration, how many sub-intervals you want, n, and then n a to b function. I mean, that's pretty much it. And then the summation in order to get you certain values. So as we go through, there's going to be many more multiple formulas and things like that, which use this sort of idea as its basis. We'll get to more points of that nature as we move in to more topics. I'm going to call it here, though, because
max 1 play per day. Free spins valid for 2 hours. T's and C's and eligibility criteria apply. 18 plus begambleaware.org.
Okay, let's go see Rhacodactylus. He's currently doing the partner push thing, so scientifically studying rhetoric and looking at politics. Oh boy. I will be back on Friday because we're still here. Next week, as of like Wednesday to the next Wednesday, we're going to go to Denmark and go check out other parts of Europe. So hope you all have a good next few days, and I'll see you on Friday or sometime thereafter. My name is Obi-Wan Pez. This is In Simplex Pachinko, and we'll catch you next time.